Structural induction is a method to prove properties of inductively defined objects, including sets and functions. This proof technique will follow the same conceptual flow as the usual induction principle, mirroring the way the structure under consideration was built. So we will first prove the induction base that the property holds for the basic elements in our inductive definition. And then we will prove the induction step. Assuming that the property holds for some elements, we will prove that it holds also for those that can be constructed from them through one single application of the inductive rule of the definition. And we will see several examples of this technique. Structural induction can be formulated in the following way. If we have a set A that was inductively defined starting from some base B, and we have a property defined on the elements of A in such a way that the following two conditions hold. On one hand, the property holds for all these elements in the base of A. And on the other hand, for an element of A that's defined in terms of some elements A1, A2, An, if the property holds for all of these A1, A2, An, then it also holds for element A. So if you have a property for which these two conditions hold, then the property holds for all elements of A. So structural induction is a way to prove properties for inductively defined sets. And the whole idea is that you are going to track this property through the inductive rules that define your set A. And I want to prove this lemma for you, and then we're going to see a number of examples to illustrate how structural induction can be used in practice. So I'm going to start my proof by defining the following set. I will define Z to be the set of elements from your universal set or full set with the property that P of A holds. And the point of this lemma is to show that set A is included in Z. In other words, for all elements of A, the property P holds. So we are going to prove that. Now, our lemma is basically saying the following two things. I'm just going to rephrase the lemma using this notation Z that I just introduced. So on one hand, the first condition says, the property holds for all elements of the base B. So using the notation Z, this is the same thing as saying that B is included in Z. Indeed, all elements of B are going to satisfy the property, so they are included in Z. And the other condition in the lemma says that, if you have elements A1, A2, An for which the property holds, or in other words, using our notation, they belong to Z, then A, which is defined in terms of A1, A2, An, for A also the property holds, and using our terminology, this is A belongs to Z. So this is just a simple reformulation of the conditions of the lemma, and obviously this is part of our hypothesis, so we are assuming that these are true. So I just want to recall, what it means that A is a set inductively defined starting from base B, and this is going to be the crucial argument in this proof. So I'm just going to recall what this part of the lemma means. So what is it that we get when we know that A is inductively defined starting from base B? So this is the definition of an inductively defined set. And it says that, the fact that you have A inductively defined from B, it means that on one hand, B is included in A. And on the other hand, it also says that, if you have an element A that can be defined in terms of some elements A1, AK, for which you know that they belong to A, then also A belongs to A. And the crucial point in this inductive definition is that A is the smallest set satisfying properties 1 and 2. In other words, for any other set X satisfying properties 1 and 2, A is a subset of X. And the crucial point here is that, you see, I just reformulated these two conditions of the lemma, And it turns out that we have right away that set Z satisfies these two properties 1 and 2. So on one hand, we have that B is included in Z, which is exactly condition 1 from here. And on the other hand, we have that if you have some elements in Z, then also this element that's defined as a composition of A1, AN is in Z. And that's exactly this condition number 2. And so the fact that A is inductively defined from B right away implies by condition 3 in the definition of A, that A has to be a subset of Z. And again, this is simply because we know that A is the smallest set satisfying conditions 1 and 2, and it turns out that Z is also one set satisfying conditions 1 and 2. And A being the smallest, it means that A has to be included in Z. And now if I'm looking again at what the definition of Z was, it includes elements for which the property holds. So this implies that P of A holds for all elements A in A. And that's exactly what the lemma was saying. So the lemma is now proved. Let's take now a few examples to show how structural induction can be used in practice. The first example I want to give is based on an example we had on a previous lecture in terms of defining what this set 3n was. And in that lecture we defined 3n to be is the smallest subset of n for which these two properties hold. On one hand, 0 is in 3n, and on the other hand, if n is in 3n, then n plus 3 is also in 3n. And moreover, we defined on this set, in one of our examples, we defined this function. It was defined on 3n, and it was taking values in n. And the definition that we gave was following exactly this inductive structure of 3n, and we defined f of 0 to be equal to 2, and f of n plus 3 was defined to be fn plus 2. And so in this example I want to show now, I'm going to prove that f of n is even for all n in 3n. And I'm going to do this by structural induction. And the structural induction is going to be following the structure of our set 3n and the definition of the function on this set. So on one hand we have the induction basis or induction base, and in this induction base we just have to check that f of 0 is even, and this is obviously true because f of 0 was defined to be equal to 2. And then in the induction step we have our induction hypothesis, which is that we are assuming f of n to be even for some n in our set. And then the point is that f of n plus 3, because it's equal to f of n plus 2, this is also even. And so then this induction step is proved, and then by structural induction it follows that our function f of n is even for all n in 3n. So that concludes the proof of this exercise. The second example I want to give also builds on a previous example we had in one of our earlier lectures, and that was about sets of words over a certain alphabet, and it was about this function we defined on words giving the mirror image or reverse image of a certain word. And I just want to define or recall the definition of sigma star. If you have an alphabet sigma, sigma star was, so is the smallest set in such a way that the empty word is in sigma star, and if you have a letter from your alphabet and a word from sigma star, then you have also that AU is in sigma star. So this is something we had in a previous example, and I'm just recalling this for you. And the other thing was that we had this mirror image function defined. This was a function defined on sigma star with values in sigma star. This was also an inductive definition of this function following the inductive structure of sigma star. And the way this was defined was that the reverse of the empty word is the empty word, and then the reverse of such a composite word this was defined to be the reverse of U times A. And what I want to prove here is that the mirror image of UV is the mirror image of V times or concatenated with the mirror image of U. And this is true for all UV from sigma star. And the way I'm going to do this is going to be by structural induction with respect to word U. So this word U, we are going to track it down through its structural definition, starting from the empty word and then going letter by letter. And for word V, I'm just going to assume it's a arbitrary word V, and we will not really look at the structure of V. So we only follow this proof by structural induction on A. So the induction base is going to be if U is the empty word, then the property we are looking at is going to be about this mirror image of epsilon times V. Now epsilon times V is V, so we are talking about a reverse image of V, and this is obviously equal to the reverse image of V times the reverse image of the empty word, simply because the reverse image or mirror image of the empty word is the empty word. So that proves the induction base of our property. And then for the induction step, we are going to take such a word U and assume that the property holds for U1, which is the shorter word. So we are assuming that the reverse image of U1V is equal to the reverse image of V times the reverse image of R, of U1. And so the property in this case refers to the mirror image of UV. And so U in this case is A U1V, and we take the mirror image. And we can see this in terms of, it's one letter A concatenated with this word U1V. So by definition, by the definition of the mirror image, this is going to be simply the mirror image of U1V times A. And then by the induction hypothesis, we have that the mirror image of U1V is exactly a reverse image of V times reverse image of U1 times A. And again, we are applying the definition of the reverse image, and we are observing that the second part, U1 reverse times A, is exactly the mirror image of A U1. And so that gives us that in the end we get the reverse image of V times the reverse image of U, which was exactly what the property is really saying. So again, this concludes our proof. It follows now that by structural induction on U, the property is going to hold for any U in sigma star, and V was anyway arbitrary, so this also follows that the property is going to hold for any V as well. The third example I want to give is about binary trees, and I just recall the definition of the binary trees. We defined in a previous lecture the binary trees over leaves. We had just two symbols for the leaves, and we had two symbols for the operators. They were just F and G. And the set of binary trees was defined inductively in such a way that on one hand you have that X and Y are trees, and then on the other hand, if you have T1, T2 trees, then you also have that F of T1, T2 and G of T1, T2, they are trees. And using this inductive definition, we had in a previous example also the definition of the height function. This was a function defined on a set of binary trees and taking values in the natural numbers. And it was defined inductively following the structure of the set of binary trees, and we said that h of x and h of y are both defined to be equal to 0, and then the height of a composite tree was 1 plus the maximum between h of t1 and h of t2 if this tree was either f of t1, t2 or g of t1, t2. And in this example I want to give here, I'm going also to define the size, the size of a tree. And the size of a tree is supposed to count the number of nodes in a tree. So that includes all the leaf nodes and all the internal nodes labeled by either F or G. So if you think about the graphical display of a binary tree, it's in terms of counting all the nodes in the tree. If you think more about this lexical formulation of the tree, is about counting the number of all symbols X, Y, F and G in the definition of your tree. So this size is going to be a function. I'm going to define it with this symbol. Is going to be a function defined on a set of trees and taking values in the natural numbers. And I will define it again inductively by saying that, the size of a tree consisting of a single node X and the size of a tree consisting of a single leaf node Y is exactly 1. And then on the other hand, if you have T to be such a composite tree, it's either F of T1, T2 or G of T1, T2, then the size function for T is defined to be exactly 1 plus, and it's 1 plus because you have one extra node, whether it's you know, f in this case or g in the other case, and then you'll have the size of t1 and the size of t2. So it's 1 plus k of t1 plus k of t2. So that's the size function defined on binary trees. And the example I want to show you here for the structural induction is to prove the following property. So I'm going to prove that the size of t of any tree is at most 2 to the power the height of that tree plus 1 minus 1, and this is for all binary trees. So we are going to do this by structural induction. And the induction base is going to be about looking at trees that are formed by single leaf nodes, X or Y. So in this case, we are going to have that. So if T is simply just X or Y, then the size of T is 1 and the height of T is 0. And obviously the condition is satisfied. We have that 1 is at most 2 to the power 1 minus 1, and so this is clearly satisfied. Now for the induction step, we are going to assume that T is of this form, either f of T1, T2 or g of T1 and T2, and the property holds for T1 and for T2. So we have that k of T1 is at most 2 to the power h of T1 plus 1 minus 1, and k of T2 is at most 2 to the power h of T2 plus 1 minus 1. So we are assuming this, and now we have to prove something about the size of T. So here are some calculations looking at this. So the size of T, this is equal by definition, by the way we define the size function, is going to be 1 plus the size of T1 plus the size of T2. And then by induction hypothesis, we have that this is smaller than or equal to 1 plus, and instead of k1, k of T1, we are going to put this expression, and instead of k of T2, we are going to put this expression. So this is going to be 1 plus, and we have 2 to the power h of T1 plus 1 minus 1 plus 2 to the power h of T2 plus 1 minus 1. And so what I'm going to do next is I'm going to say, look, instead of h of T1 and instead of h of T2, I'm going to put the maximum between them. So I'm going to go from a value to another value which is larger than or equal to. So I'm going to obviously have that this is smaller than or equal to. I'm going to have so this 1 and this minus 1 cancel, so I will have this term and minus 1. And for this term, instead of h of T1, I'm going to put the maximum between h of T1 and h of T2. So this is going to be 2 to the power max between h of T1 and h of T2 plus 1 minus 1. And For this one, I'm going to do exactly the same thing. Instead of h of t2, I'm going to put a maximum between h of t1 and h of t2, and I'm going to end up with exactly the same term written one more time. So this is going to be 2 times this much. And this is now equal to, by definition, this is going to be, the height of t. So if I'm pointing this out, 1 plus the maximum between h of t1 and h of t2 is exactly the height of t. So what I'm getting here is that this is exactly 2 times 2 to power height of t minus 1. And this is obviously equal to 2 to power h of t plus 1 minus 1. And so that concludes the proof of our induction step. We started with the size of t, and doing a number of calculations, we ended up with the conclusion that the size of t is smaller than or equal to 2 to the power the height of t plus 1 minus 1. And that's exactly the property that we had to prove. So again, by structural induction on the set of binary trees, we get that this property holds for all binary trees.